Good afternoon and welcome to Information Retrieval. We start a new module today, a new topic. The topic is called decision trees. So there are decision trees. Um, and here's the first new thing to learn. This thing that we have over here, this is called a decision table. And here's the idea, here's the problem of what we are trying to do. We have four variables over here. Okay, and the variables are called outlook, temperature, humidity, and windy. And these are called the independent variables. And somehow or other, they determine this thing over here, which is called the dependent variable. So what we are doing in this particular problem here is we're trying to decide if we play tennis. Now notice this is a yes-no variable over here, a Boolean variable. It could be true, false, just the same. So there's a little bit of vocabulary here that we have to do. First of all, notice that we are making a very big assumption, or I should say there is a hypothesis that we are making here. And the hypothesis looks like the following, that we are somehow saying that play tennis is a function of outlook and temperature and humidity and windy. Now, this is the goal here is to figure out what this function is. So the goal is to figure out function f. And when I say function f, I'm referring to this one over here. Now notice what's going on here is we have sampled data. We have labeled data. So that means that this is an example of supervised learning. We have labeled data. So this is an example of supervised learning, meaning that we have some instances of labeled data. Labeled means we have the desired output. And what we would like to be able to do is generalize this so that we could extend this to situations that we haven't seen before. That is the goal. Now, there are a couple of things to point out here, and some of this is a vocabulary. Now, first of all, notice I said over here, this is a hypothesis. In other words, we are guessing whether this individual person, whether they play tennis or not, is a function of these four input variables. It may be the case that our hypothesis is completely incorrect, and that's something that you need to consider as you're going about and analyzing all of this. Okay. The other thing that we need to talk about here is we need to talk about the type of data. Now, first of all, let's get to a new slide here. There are a few things to note here. First of all, we note that Outlook can assume one of three values. It looks like it can be sunny, overcast, or rainy. And we come over here and we look at temperature. And temperature can be hot, mild, or cool. We look at humidity. And humidity can be either high or normal. We look at windy, and windy is either true or false. And then we look at the variable we're trying to predict, play tennis, and that's either yes or no. So the first thing to note here is that all data is discrete and finite. Okay? Notice over here in this entire table, we don't see a number anywhere. So data scientists, AI people, they have a word for this. They call this nominative data. They also might call it discrete data. They might also call it finite discrete data. All of these three words, or these three terms, mean exactly the same thing. And as we go about and talk about decision trees and decision tables in here, we are initially going to assume that we have nominative data. Okay, later on, we are going to extend this to the case where there might actually be numbers in here. For example, it certainly makes sense that the temperature might be a number. Okay, so when we stick numbers in here, we would say that we would have real valued data. So one of the things when you're talking about various machine learning algorithms, data mining algorithms, you have to talk about what kind of data can the algorithms work on. And initially for this case, we are talking about discrete data. Okay, let's take a look at this table again over here. And one of the things I want you to note is that the dependent variable, my pen is not working, there we go. The dependent variable over here is Boolean. Okay, or it's yes, no, which is essentially the same thing. And a lot of people get the feeling that decision tables are only good for when the dependent variable is Boolean. And that's not the case. Consider the following situation. Suppose I have some decision table over here, and I don't know, I have variables here. I'll have color, and maybe color can be red, blue, green, and maybe I have weight, and weight could be heavy or light, and I don't know, I'll make something up here, far-sighted. So far-sighted can be yes or no. And over here, I have classification, or I'll call it type. There we go. And type can be animal, vegetable, mineral. And again, what I am assuming here now is that type is equal to f of color, weight, and farsighted. I'll just call it fs, like that. Okay, and we can imagine that this table, we have a table with some data in it, and we're trying to figure out what f is. Now, one way that we could think about this is instead of trying to figure out f, instead what I try to figure out is I come over here and I go, is animal. And this could be is vegetable. And this could be is mineral. So that if we came over here and the type over here was mineral, then what happened, this would be false, false, true. And if this was vegetable, then this would be false, true, false. And now what's happening over here is we could say that instead of trying to guess this function f, we could call this function g, we could call this function h, we could call this function j. And what we're trying to figure out are these three functions. In other words, what I'm trying to say here is that if this is nominative, remember what that means, a finite class, okay? We could actually reduce this problem to a bunch of Boolean variables, okay, that are our output variables or our dependent variables. We're going to see later on that we don't even need to do that. So the whole point that I'm trying to make is that the output variable here, okay, this can be multi-valued. Multi-valued, not just Boolean. And for that reason, decision trees can be used for classification. Something we talked about in naive Bayesian inference. So this is another way of doing classification. Okay, so I hope everybody's clear on that. Let me save this. So here we are back at our table. And let me come over here and number these. 1, 2, and so now the question is, figure out f. Figure out the function f that we spoke about before. And before we get to the more elaborate, complicated stuff, I'm going to give you a couple of simple ways to figure out f. And you might look at this and think, well, that's really goofy or silly. And I'm going to say to you that, no, it isn't. See, here's the thing that you have to consider when you go out and work on problems like this in the industry, okay? And basically, it's expensive to build models. It takes time. The boss comes in and says to you, here's some data that I have here, and I want to predict playing tennis. You're some high-paid data professional. You've got teams of people working for you, and it could take a very long time for you to figure this out. Well, that's costing money. So there are, when it comes to building models and trying to figure out this function f, there is always a tug and a pull between elaborate versus cost. You could be very elaborate, and elaborate hopefully means that it's going to be more precise, but it's going to be more expensive and it's going to take more time to figure that out. So to give you an example here, I'm going to give you algorithm 1. And algorithm 1 is called majority rule. And it's really, really simple. I come through here, and first what I'm going to do is I'm going to count no. So it's 1, 2, 3, 4. I see 5 no's. And if there are a total of 14 of these, that means there are 9 yeses. So the majority rule says, always say yes. Okay, that's really, really simple. And what's the accuracy of it? Well, in this case, it would be 9. It gets it right 9 out of 14 times. That's not bad. That's better than half. If I were to call up my calculator, let me see if I can do that. If I go 9 divided by 14, I get that that's 64% of the time. And who knows? That didn't take me a whole lot of time to do. The boss may feel that 64% of the time is a perfectly reasonable thing to do. For a perfectly reasonable way to do it. So that's algorithm number 1. So here is algorithm number 2. And algorithm number 2 has a name, and it's called OneRule. And here's the way that OneRule works. OneRule works by saying, let's look at each one of the individual independent variables. So here's Outlook. And Outlook can be sunny, or Outlook can be overcast. Outlook can be rainy. So I come over here, and for sunny, let's see, I have sunny, no, and I come down here, and here's, okay, so there are 3 no's for sunny. So now there's 1 yes, so that's 1 yes and 3 no's. Here's another yes, so that's 2 yeses and 3 no's. So this gives me 2 yeses, 3 no's. And if I look at overcast, I get 1 yes, and I get 2 yes, 3 yes, 4 yes. And I look at rainy, and that gives me 1 yes, 2 yeses, 1 no, so that's 2 to 1. And I come down here, and that is 3 to 1, and this is 3 to 2. So that gives me 3 yeses and 2 no's. And from this, I make the following rule. I say if pardon my penmanship here, if Outlook equals sunny, I'm going to pick the majority of this, and I'm going to say then no. Else, if Outlook equals overcast, then no. Else, if output equals rainy, then yes. Okay? And what I want you to note is that over here, this was correct 3 out of 5 times. This was correct over here 4 out of 4 times. This was correct over here 3 out of 5 times. So the accuracy of this rule that I just wrote right over here is 3 plus 4 is 7, plus 3 is 10. Okay, so that means I got it right 10 times. The accuracy is 10 out of 14, which is better than I got with majority rule. Is everybody okay with that? Well, we're not done. What we've done here for outlook, we now need to do for temperature, humidity, and windy. So let me see how clever I can be in keeping all of this information up here while we figure out the other rules. So let's come over here, okay, and let's figure out the one rule for temperature. So for temperature, okay, so for temperature, it can be hot, it can be mild, and it can be cool. And when it's hot, let's see, I've got 1 no, 2 no, 3 yes. So this is 2 to 1 for hot, and this is 2 to 2 for hot. So I got 2 yeses and 2 no's. For mild, I got a yes, a no, so that's 1 to 1. This would be 2 to 1, 3 to 1, 4 to 1, 4 to 2. 4 yeses, 2 no's. And when it's cool, I got 1 yes and 1 no, so that's 1 to 1. Here is 2 to 1, 3 to 1. So I got 3 yeses and 1 no. This better add up to 14. Let's see. 2, 4, 8, 10, 14. So my rule here would be if temp is equal to hot, now here it doesn't matter which one I take, okay? So, and what is the, oh, I just say yes or no. So I'm going to come over here. So I'll say then yes. Else if temp equals medium, then yes. Oh, well, this is interesting because watch what we can do here. Else if temp equals cool, then yes. So it looks to me that I could just come over here and just say yes all the time. Okay, how accurate is it going to be? Well, I'm going to get 2 plus 6 plus 9. This is 9 over 14, which is just what we got with majority rule. Notice that this is not as accurate as Outlook. So far, Outlook is good. I'm going to come over here and do this for humidity. And humidity, I can be high or normal. So if it's high no, that's 2 no, that's 1 to 2, that is 2 to 2, that is 2 to 3, that is 3 to 3, that's 3 to 4. So I got 3 yeses, 4 no's. Over here under normal, I've got 1 yes, 1 no, so that's 1 to 1, 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1. So that's 6 yeses, 1 no. So my rule would be here would be if humidity equals high, I pick the bigger one, then no, else if humidity equals normal, then yes. This one over here has an accuracy of 4 out of 7. This one over here has an accuracy of 6 out of 7. So 4 plus 6 is 10. So this has an accuracy of 10 out of 14. And this one has the same accuracy as Outlook. And finally, we come over here and we do windy. Let me see how I can do this. I'll say OK. I'm going to come over here and put this over here. And we're going to say windy. So windy, we could have false or true. False, that gives me 1. That's 1 to 1. That's 2 to 1. That's 3 to 1. That's 3 to 2. That's 4 to 2. That's 5 to 2. That is 6 to 2. 6 yes, 2 no. And if it's true, that's 0 to 1, and that's 0 to 2, and that's 1 to 2, and that's 2 to 2, and that's 3 to 2, and that appears to be 3 to 3. I hope I got that right. That's 6, 7, 8, that's 14. So it looks like over here we would say if windy equals false, then no, else if windy equals true. And you could pick either one of these that you want. You could say yes or no. Now, it might be fun to say no again, because then the accuracy of this one over here is 6 out of 8. And the accuracy of this one over here is 3 out of 6. And the total accuracy that I get over here is 9 over 14. So we can see that windy is not as accurate as humidity, okay? So we can see that basically that the humidity one rule and the outlook one rule are slightly more accurate than either temperature or windy, and both of these are more accurate than majority rule. So the question is what do you do in a tie? And the answer is you can pick either one you like. Now, there is a principle in data mining and AI. There's something called Occam's razor. And that's a cool term to throw around. Use it with your friends. They'll think you're really smart. And Occam's razor says that whenever you have two explanations for a phenomenon, pick the simpler one. So the question is between these two rules here, and I'm looking at this, which rule am I right here? I'm looking at humidity and I'm looking at the outlook one. Well, there are two different outputs here. There are three different outputs here. Occam's razor might say pick the simpler one. Well, humidity has less branches coming off of it. Okay? So the point is I want you to note here that one rule is still something that is relatively easy to implement. It's a little bit more complicated than majority rule. It's going to be a lot less complicated where we're going next, which is decision trees.